Okay, welcome to note set number 28. We're going to be talking about discrete time filters in particular. So that's when we use a discrete time system, particularly to you know, remove or influence certain frequencies for like audio, or we've seen communication systems use these ideas. And we're going to talk about both ideal filters as well as practical filters. So we're going to start getting into some of the ideas that you would use to think about these filters and even start to think about designing them. So we did talk about some of this in the continuous time case. So in the continuous time case, we can specify filters. We looked at the ideal filter for the continuous case. Here we're going to do that same kind of thing for the discrete time case. So for the ideal low-pass filter, you can see that we have specified a rectangular function that passes frequencies from minus B to B, and then outside of that stops those frequencies completely. So we say our cutoff frequency is B. You'll notice that outside the minus pi to pi range, this thing completely repeats periodically. It has to, because h of omega is a DTFT. We also see that we have a linear phase response. That's just like for the continuous time case. That would be the ideal phase response that we would want to have. And as always, we only need to look at the minus pi to pi case as we just mentioned. So just like we had for continuous time scenario, there's low pass, high pass, band pass, and band stop. Those are the four main categories. There are others, but those are the main ones that you'll run up against most often. So just like we did for the continuous time case, we ask, gee, could we actually get such an ideal filter? And the answer is, again, despite the power of discrete time, no, we can't. And the main reason is that it's non-causal. So it's not really possible to make a filter that is non-causal. So we can see the same kind of thing that we did before. We've got the rectangle here to represent that ideal magnitude response. We've got the e to the minus j omega n sub d to represent that linear phase response. And now we're going to apply a delta function to find the impulse response of this filter. And when we do that, this is just like we saw for the continuous time case. We recognize that this does nothing more than imparts a delay of nd samples. And so we can look on our DTFT table. Again, remember, this machinery is just to create the repeats. So we see that on our table, and we recognize, okay, our impulse response before this delay is this sinc function, and then after the delay we have included this n sub d here. So to look at a picture of this, our delta function hits at time equal to n0. It's 0 prior to that, 0 after that. So if the system is causal, the first time it can start to respond is at n equal to 0, but we see that it starts at actually time equal to minus infinity. How does it know to do that? Well, it's impossible for a real system to know how to do that. So we can't have such a filter. So can't have an ideal filter, and so the question is, how do we get close enough, or how close can we get to an ideal low-pass filter? So we've already tried looking at filters like this. This was an n-point moving average, and we saw that that was a really bad filter. We just take n sequential points, input samples, add them together and divide by n, move forward to the one sample to the next set of n points, do the same thing over and over and over. So we need something different. Now, we just saw that the sinc function, a shifted sinc function, seems to be involved in making the ideal low-pass filter, and the problem was all the stuff down here. So what we could do is actually just truncate that and throw that all away and say, all right, those are all going to be zeros, and assume that we have zeros up here, and think about an impulse response like that. By doing that, we come to the conclusion that we can actually set our B coefficients in this kind of filter. Instead of setting them all to 1 over n, we can set them according to these numbers which are in this sinc function. And so let's take a look at doing that. So we define our filter coefficients for a non-recursive filter like this up here. Instead of setting them all to 1 over n, we set them according to these numbers. So here's the equation for how we would do that. And so let's take a look at that. So those numbers go into this non-recursive causal filter, and let's see what we get. We can very easily write out what the transfer function looks like and what the frequency response looks like, and we can use freq-z to calculate these. I'm trying to design a filter here, ideal filter with a cutoff frequency of 0.6, and so I've done this for m equal to 20, m equal to 60, and m equal to 120. So now let's remind ourselves, what is that m? It's the order of this. So we go from m equal to 0 out to capital M. So we say that we would actually be using 21 coefficients, 61 coefficients, and 121 coefficients. Now, as we do that, we see a couple things happening here. When we look at these three different examples, we see that as we go to longer lengths, we do tend towards a better and better low-pass filter. I mean, this bottom one looks pretty good. We've got a nice sharp transition, but there's a few things that are bugging us about this here. We see these wiggles here, and we see these wiggles here. And if we were to plot this in dB form, those wiggles, especially those down here in the stop band, would really be bothersome. So let's take a look at this, plotting our magnitude of our frequency response in dB. And so I'm looking at the m equal to 30 and the m equal to 120. Even with 121 coefficients, we see that our stop band at best is getting down just below minus 40 dB of attenuation. Now, and that's all the way out. Near closer into 0.6, we're only getting about 30 dB of attenuation. So really, this is not a very good filter. It's not horrible, but it's not bad. Now, for discrete time filters, in practice, when we're really trying to assess them, we will always want to plot them in dB. Sometimes, for overriding reasons, we might want to look at them briefly in non-dB values. Now, the funny thing is that for discrete time filters, we hardly ever use a log frequency axis. Now, occasionally we do, but for the most part, we plot them just between minus pi and pi. And again, I'm doing my trick of normalized, so minus 1 is minus pi. So these are not bad filters, but we can do better. So let's talk about specifying practical filters, and then we can talk about ways of trying to achieve our specifications. So for that filter that we just looked at, what we saw was that there was some ripple in the pass band. So we can specify, and on the diagram on the vertical axis, I'm specifying this in non-dB, but we can specify a range, this delta p that is plus and minus from 1, and we can then convert that into a dB value like that. And so that's called our passband ripple, and if we convert it into dB like that, we would be talking about how much ripple up and down in decibels that we would be seeking for our design. So it's not uncommon to see things like 1 dB of ripple, or even less, maybe 0.5 dB for a really good filter, 0.1 dB for a really good filter. Now the second thing is the amount of attenuation out here in the stop band. So we want to make sure that our frequency response in the stop band never pops up above this delta S value. So on the diagram I'm showing that in non-dB, but we would convert that into attenuation. Now we put a negative sign there so that we know that delta S is a small number, less than 1. When we take the log of that, we get a negative value. Since we're calling this our stop band attenuation, we put a negative sign there to convert it into a positive number, so that we say if this level here is minus 40, we would be saying that we have a 40 dB amount of attenuation. So it's just a matter of semantics, really. We would be saying we have minus 40 dB gain in our stop band, but 40 dB of attenuation. And so we've specified what happens in the passband as far as ripple goes, and where we want the passband edge to be. We've specified the amount of attenuation in the stop band, and we can specify where the stop band edge should be. And the region between those two edges is called the transition band. So ideally, we would like to make the passband ripple go to 0, the stop band attenuation be down as far as possible, so 0 in non-dB, and a extremely large decibel value, and we'd like to make this transition band as narrow as possible. So those would be our design goals as we go through this. Now we've got a few others of these. I'm going to go through them a little more quickly. This would be for the high pass. All the same things are there. It's just that the pass band now is over here, so we're passing high frequencies from some cutoff up to pi. Remember, there is really nothing beyond pi. It's just a repeat of the same old story. So we can only pass up to pi. We've got our band pass filter specifications. Now we have 2 different stop bands, 2 different transition bands, and there's no reason that those transition bands have to be the same width. And then we have a band stop specification. Again, now we have 2 pass bands, still 2 transition bands. Those all can be spec'd independently from each other. Now, what we'll see is that as we make these filter specifications, as we move them towards a more ideal scenario, it's going to be harder to achieve that with practical filters. And as we look at some of these designs, it will become clear what we mean by harder. So we just saw that by making our non-recursive filter longer and longer and longer, we can get a better and better filter. When we spec these things, we may discover, if we make our transition band really narrow, our passband ripple very small, and lots of stop band attenuation, we may discover that we need a really long non-recursive filter to achieve that. That would mean a lot of computation, and that would be a drawback to that kind of design. So let's talk about these different types of filters. We've been talking about non-recursive filters, and really there are 2 main types, aside from the low pass, high pass, but we're talking about the structure of the difference equation. So we have recursive filters. They have all these terms in them that account for the feedback that we've talked about. So recursive filters have feedback. It's that feedback that requires them to be recursively computed. And we can see when we group all of those over on the right hand side, we now have that in a recursive form. Non-recursive filters have no feedback in the difference equation. We have only one y of n term over there, and everything else is an input term. So there's no feedback in those, and they do not need to be computed recursively. We've already seen a picture for the block diagram for a general difference equation, and since the general difference equation does have feedback in it, that would correspond to the recursive filter. And so we have all of these components here contributing those feedback terms. Now if we were to set all of those coefficients to 0 to make this term go away, we're left with a non-recursive filter, and we'll take a look at that in just a little bit. So we know how to write the transfer function in both z inverse and z form. We know how to write the frequency response. We know how to find the pole 0 diagram. And the important thing here is, because recursive filters have feedback, they can have poles that are not at the origin. So I'm showing a couple poles here. And since they are not at the origin, if we're not careful, those poles could end up outside the unit circle, which would then cause this filter to be unstable, and that would actually be an unusable filter. So we want our filters to be stable. And then we also have this issue of poles or zeros at the origin, depending upon this term out here, whether n and m are equal or n and m differ from each other. Depending on which one is bigger will tell us whether we have poles at the origin or zeros at the origin. But a key thing about recursive filters is they can be unstable, and they are the only way to get poles that are not at the origin. So for this particular diagram, regardless of what we have at the origin, because if you remember we said poles and zeros at the origin don't affect the magnitude. So I'm plotting the magnitude over here, and these poles here, as we've seen, contribute to these spikes near the angle where those poles occur. But we also see a 0 right here. That's at an angle of 0, and so that's a discrete time frequency of 0. And you'll notice that the frequency response is tagged down, is actually pegged down to 0 at that particular frequency. So again, it's important to keep in your mind that this discrete time frequency omega is tied to the angle around the unit circle. Remember that Burger King crown that we unfolded. Non-recursive filters, like I said, we get rid of this term, we get rid of all of these things, so now we end up with this as our difference equation, and all those feedback terms, well, those are all gone now. So we have only so-called feed-forward terms, and very easy also to write out the transfer function of those. It'll be a single polynomial in terms of z inverse, and then if we convert it into the z form, we'll get a bunch of z we'll get a z to the m down in the bottom. And so what that tells us is that we will end up with some poles at the origin, m poles at the origin. Converting from here into the frequency response, we get a very simple structure for the frequency response. Again, all of this can be evaluated with the freq command. So now notice when we look at this form of our transfer function, we've got a polynomial in the numerator, so the only thing that can give us is a bunch of zeros, and the only poles we can get come from here. Those poles are going to be at the origin, so we'll have m poles at the origin. So because there's no feedback, the only place we can have poles, or the only place the math tells us we get poles, is at the origin. So consequently, such filters, these non-recursive filters, have the nice property that they are always stable. So with the design of non-recursive filters, we can optimize these things to our heart's content without having to fuss about, gee, I'm tweaking those to try to get the best frequency response, but I don't have to worry at all about, am I causing this filter to become unstable? So that's a really nice characteristic of these things. And then for this particular system, I'm showing the frequency response here. And because there are no poles other than at the origin, we don't see any really sharp peaks. We do see this in the center here. You'll notice that when we're not tacking something down, the mathematics can really show this, but unlike a real tent, that if you don't tack it down, it does just kind of flutter down to the ground. Our magical tent here, if you don't tack it down, it is going to try to go up to some degree. So because we don't have any zeros close to the origin, or close to omega equal to 0, we do get a little bit of a hump there, but it's not coming from a pole. But we've got a couple zeros here that are causing these things. And then really obvious, we've got a couple zeros right on the unit circle, so that as we walk around the unit circle, bam, we hit the 0 and we go directly right to the ground. And likewise over here, when we get over to here, we're walking right there, and bam, we're tagged right down to the ground. So those are some nice characteristics of non-recursive filters. Now, you may hear the words, or the acronyms, IIR and FIR filters. These are just new names for the same two categories of filters we just saw. So IIR stands for infinite impulse response, and FIR stands for finite impulse response. So infinite impulse response means we have an impulse response that goes on for infinity. Not in the negative direction, because we want these things to be causal, but in the positive time direction. So once you hit it with that impulse function, this impulse response just kind of rings like a bell, but rings forever. Whereas an FIR filter, you hit it with the impulse function, and the impulse response starts to do something, and then bam, it goes identically to 0 and stays at 0 for forevermore. So recursive filters are IIR filters. If we look at our our transfer function, think about breaking this down into its factors, and we'll just assume for simplicity here, no repeated roots, no direct terms, and then do our partial fraction expansion, do the inverse Laplace, we'll get terms that look like this. And you can see that each one of those terms basically lasts forever. It's a decaying exponential. P1 has to be inside the unit circle, so its magnitude is less than 1. So it does decay, but it'll never go directly completely to 0. On the other hand, if we were to take the inverse Z transform of this, well, we look at this, and this really is the sum that occurs in a Z transform. So we can actually show that the impulse response, h of n, consists of a bunch of zeros up till time equal to n equal to 0, and then we just start seeing these coefficients right in order, and then bam, back to 0. So yes, indeed, these non-recursive filters are FIR filters. That is a fact. So we'll stop there. We've got a little bit of insight now to filters and pole zero diagrams and things like that. Thanks. We'll see you in the next one.